In our dimensions, we oftentimes have hierarchies included, and therefore we want to talk about how we should deal with those hierarchies. So what is the best way to go about them? Because there are also some pitfalls that we can fall into, and that's why we want to talk about the best way of dealing with hierarchies in our dimensions. In our source data, the data is used for transactional processing. And this is why the data is oftentimes also normalized. That means that if we have, for example, this product table, we have the associated category also, and then there is a separate table. This, of course, saves disk space and is also good for the write performance, and therefore it is just a good fit for transactional data processing. But for us, since we want to use the data warehouse for analytical data processing, we are looking for high performance to read the data, so to get the data out of the warehouse, and also we want to have a high usability. And if we would have such a case where everything is denormalized, we have many foreign keys in our table, and this can really make the fact table very wide. And this is something that we should avoid. If we do that for all of the different dimensions and all of the hierarchies, we get something that is called a snowflake schema. So we have only this product name as a dimension, and then we have another level of hierarchy, so we can connect the hierarchy from the product with the category via this column, and then this basically looks like a snowflake, and therefore this is called a snowflake schema if all of the dimensions are denormalized. But this is something that should be avoided because we really don't have any benefits with that for our data warehouse, because we just have a lower performance and a worse usability. And therefore, we should not do that. And even there are some people that are, especially the ones that are a little bit more experienced in data modeling, they have the kind of habit to normalize the data. So even if the data is not normalized in the source data, they tend to, because it is good for certain cases, normalize the data. But this is not the case, as we've learned in the data warehouse. And here we should really resist that habit to normalize the data because it's bad for usability and we should avoid it. Instead, we should try to flatten the data. So we should try to denormalize the data. And this is now the way to go. For example, we could just create a join between category ID and then the category table. So we could write the data in our data warehouse just in one table, and like this have flattened the dimension. This is what we should do in our dimensions in dealing with these hierarchies. And what we can do as well is we can combine attributes of different levels of hierarchies together in one column. So this combination can be then more user-friendly if the user wants to also have the combination of, for example, year and quarter, and then this can be used directly out of the box. And especially this can be helpful if we have duplicate values, or let's say Nashville, a city that can occur in the state, and not only in one state, but the same city also in another state. In that case, it can also make sense to have some pre-calculated column that is just combining the city and the state, especially in those cases where one attribute can occur in different levels of the hierarchies multiple times. In that case, it can especially make sense for the user friendliness to just create an out-of-the-box combination of those two columns. So these are things that we should keep in mind, but the most important thing is we should try to combine those hierarchies and collapse them into one table when it makes sense. So we have less dimensions and a more flattened table. So this is how we should deal with hierarchies in the dimensions. In this lecture, we want to talk about conformed dimensions. A conformed dimension is a dimension that is used for multiple fact tables or multiple stars. And the purpose for those is to compare multiple facts and use them together in one report or in one analysis. So we want to compare facts across multiple facts. So let's imagine we have a sales report, we have a star schema, so a data mart around a sales table, and in our case we now want to also analyze the costs. So we have a second fact, and now we want to compare, of course, the sales with the costs. And now what we could do is use a so-called conformed dimension. So a dimension that shares the same attributes. So for example, this is something that can be the date or the time, which is the most typical example for a conformed dimension. And now with that connection, so this conformed dimension, we can now create a report or analysis that is comparing the sales and the fact. So we call this a drill across. Another example of that could be that we want to just use the region as a conformed dimension. So for example, both in the sales table and in the cost fact, we have the region included, and these are now both attributes that are shared by both of these facts, and now we can, in one analysis, in one report, use the sales and compare it also with the cost using this shared attribute of the region. So let's have a look at the following example. We want to use a conformed date dimension. That means we use the date, so a shared attribute which is available in the cost and the sales, to just compare the cost and the sale. And we can now do that because we have both facts connected with this date dimension. And with that, the result of that is that we can use this drill across, meaning that we can compare facts, so measures, from those two independent fact tables. So even though they are separate fact tables, we can now compare those values with each other. Another example would be to use a conformed region. So in that case, we have the shared attribute of, for example, the country. And in that case, we can again compare the costs with the sales in our case. So the measures of those two fact tables. Of course, what we need to have if we have a conformed dimension, we need to have the identical attributes, or at least a subset of attributes used for both of these facts. So this could be, in our case, if we have the sales fact, that we of course have a date foreign key, and then also in the cost fact we need to also have this date foreign key included. And note that it is not necessary to have the same granularity. So for example, in this case, the cost fact is one row and one day. So therefore, every foreign key, so every value here is also unique. So one row is equal to one day, and this is not necessarily the case in the sales fact table. So in that case, here there can be duplicate values and there can be a different granularity. And this makes now this conformed dimension so powerful, because now even though we need to have separate fact tables, we can still compare those values with these conformed dimensions. Another option would be that we can also have, in this case, only the monthly costs, but in the sales table we have maybe just transactional, or also we have just a periodical sales fact, so every day is one row. But in this case, we can still have different foreign keys. So for example, we can have just the foreign key, in this case, that is using the month and the year to connect to the dimension, and in the other case we can have the daily key. So this is using now different foreign keys, but still it is possible to use this same dimension. And then only, of course, in the cost fact we need to be careful to use only the correct dimension attributes. So this is possible to use also different foreign keys, but also, for example, if we have a monthly value, another alternative would be to just use the first of the month and still use this foreign key. This is also something that is possible, but I would personally prefer that if we have the other foreign key also created in our dimension, that we then use that one of the month. So this is how we can use this conformed dimension to drill across and use multiple fact tables together in one analysis, in one table, or in one report. And therefore, if we want to have multiple facts, it is good to have those conformed dimensions in our data model. Sometimes we have a dimension in our data model that is not really a dimension. So this dimension does not have a separate dimension table, but still it functions in a way as a dimension. And that is a so-called degenerate dimension. Let's assume we have the following transactional sales fact table. In this case, we have different transactions and there are different amounts, and they can be also summarized together in one payment. So we can have a payment foreign key and a payment dimension. But sometimes all of these relevant attributes have already been extracted by other dimensions, or sometimes also this value of the header is not really important and therefore we already have all of the relevant information. In that case, we are left only with the primary key of this payment dimension. So of course, in that case, it doesn't really make sense to have this separate dimension because there's no additional information. And therefore, this can be still important that we, even though we don't have this dimension of the payment, this value of the payment ID can still be of value for our analysis. For example, we want to summarize the amount of each of the payments, or we also want to maybe calculate the average of the payments, so of the amount of the payments. And therefore we need to be able to group also by this column. So in that case, we would not have this separate dimension table, but we would keep the value of this fact table of, in this case, the payment foreign key. Yet, of course, in that case, it is not a foreign key anymore, and we should also denote that. So we should explicitly make it clear that this is not a foreign key and that there's no dimension table associated with that. And therefore, we could also just add the suffix, in this case, for example, DD. So this is suggested by Kimball, and this is what we can do as well. So we just have to denote that this is a special type of dimension, so we don't have a foreign key, and this is not referencing a real other dimension table, but still it can be of value and it can be used in the analysis. So we've learned that a degenerate dimension is a dimension key only, so only the dimension attribute in our fact table without the associated dimension. So this can be, for example, a payment ID or anything else that is just something that has no associated dimension table. So this mostly occurs in transactional facts, and oftentimes this is something like order IDs, billing numbers, or invoice numbers that already have all of the other information extracted, and we therefore are left only with, for example, the order ID, but still it can be a relevant attribute, and therefore we keep it even though there is no additional dimension attached. So that's why it can be important to still have those degenerate dimensions, even though there is no other dimension table attached to it. Sometimes in our transactional fact table, we can have a lot of indicators or flags that are actually dimensions, but they don't really fit into a given dimension. And therefore we could create a so-called junk dimension. But now let's have a closer look at when these junk dimensions could appear and how we should deal with them. So therefore, let's have a look at the following example. In our case, we are looking here at a transactional table. So there are some sales transactions and we have a few flags or indicators. So for example, what is the payment type? Is it incoming or an outbound payment, and also is it associated with a bonus or not. And in this case, we have now a few options of how we could deal with these dimensional attributes in our fact table. So first of all, what we could do as data modelers, we can suggest that we can just eliminate them if they are not relevant. But of course, there might be some business users that say, this is very relevant for me and I still want to use these indicators. And in that case, we can, if we want, of course, leave them in the fact table. So of course, this could be also an option, so it's like a dimensional value, but we are still just having that in the fact table. This is possible if it's just an indicator and we don't want to create an additional dimension for that. But now, what happens if these are very long text values that are really bulky, and then also it could be that the table size, if it's a very long fact table, is just increasing dramatically, and in that case it would also not be a really nice situation. Of course, what we also could do in such a situation, we can create a dimension. So for one of these indicators we can create one separate dimension. But of course, now again, the problem with that would be that if we have already a very wide fact table, this could just again increase the size and the width of this fact table, which is not so good for the performance and not so good for the user friendliness. And therefore, we can go also with an alternative, and that is to create a so-called junk dimension. So first of all, what is a junk dimension? A junk dimension is basically a separate dimension that contains various flags or indicators. So this could be yes, no, or anything else with a very low cardinality. So the options of values are not so many. So for example, there are only 2, 3, or 4 different values. And then we refer to this as a junk dimension. So we can understand this junk dimension like a box in our household where we just put in some items that don't fit anywhere else. So we don't want to create a separate storage location for these various items, and therefore we put them all just in one box. So we have here all of the items that don't really fit somewhere else. And this is how we can also think of a junk dimension. And before we have a look at an example of how this can be implemented, we also quickly want to note that the expression junk dimension is usually only used if we talk to other BI consultants, other data modelers. Of course, if we talk to our customers or to the business users, we usually don't want to use the term junk dimensions, because with that we could just make them believe that the data is junk in there, and therefore we would use a nicer term. For example, we could use transactional indicator dimension or transactional flag dimension. So like this, we can also talk to the business users and we don't have to use this word with junk in it. So this is what we can do if we talk to the business users. But now let's have a look at the example of how this could be implemented. Let's assume we have the following fact table. We see we have these 3 indicators. And now what we could do is just replace them all with a foreign key. So in this case, 1, 7, and 12. And of course, we now need to create all of the possible combinations and have also this flag primary key. So in that case, we can create the reference from the fact to the dimension. And then we have all of these possible combinations in this dimensional table. And now, of course, this can be used very easily for the users. So we can use the payment type to group the data by the amount. We can use the other attributes such as the bonus and so on. And this is our goal with our dimensional modeling. So this works now very well. But now we have to be a little bit careful, because sometimes there can be quite a lot of combinations. Assume, for example, that we have in this case 3 different columns, and in the first one there are 3 potential values, in the second one only 2, and in the last one also only 2. In that case, we have a total number of combinations, which is 12. So of course then our dimension table should have now 12 rows to reference all of these different combinations. But sometimes if we have a lot of values, so a lot of indicators, this can increase exponentially. So we can end up with a lot of combinations. For example, if we have 9 indicators with 4 dimensions, we have over 260,000 combinations, and this would be a table that is really, really large, and therefore this is not always a very good situation. So how could we deal with the situation of many indicators with maybe a lot of combinations in total? So in this case, we could only extract the combinations from the fact table that have actually occurred and disregard all of the combinations that in practice would never occur. And we can see that by just extracting the available combinations from the fact table that have already occurred in the past. Of course, we have a little bit the risk that there might be some new combinations that are maybe super rare and that have not been created or have not been occurred in the past. In that case, what we could also do is to just split up these dimensions into multiple chunk dimensions. So for example, if we, instead of putting them all of these 9 indicators in 1 dimension, if we put them in 2, we get a lot lower number of total combinations. For example, the one with 5 indicators, we have only in total a little bit more than 1000 combinations. So in such a situation, if we have a lot of indicators, we could also split them up into multiple dimensions. But in general, these chunk dimensions can now be used to just have all of these indicators or flags that don't suit in other dimensions. And that's why those chunk dimensions can also be useful when we want to model our data. In this lecture, we want to talk about something that can happen especially with our date dimension. So again, the date dimension is, we know, the most important dimension, and there can be, of course, in some facts, multiple date keys. And then our date dimension can play multiple roles. So let's dive into how we can work with these so-called role-playing dimensions. So first of all, what is a role-playing dimension? So a role-playing dimension is a dimension, as I mentioned, usually the date dimension, that is referenced in a given fact table multiple times. So let's have a look at an example. In this case, we go back to our production table. So in this case, we have one fact table that also contains order dates for specific products, and then also when we started with the production of those products. And we can see now that we have 2 date foreign keys, and now of course we have 1 date dimension. And now it wouldn't make sense to duplicate this dimension physically in our database and have now 1 dimension that is for the order date and 1 dimension that is for the production date. And therefore we can use that same table but now with different roles. So we can create, for example, a join or a relationship to this same date table but in 2 different ways. So in the first one, we use that date foreign key, and in the second one, we use that production foreign key. And now the first role is just the order date, and then the second role that this date dimension plays is the production date. So these are now the 2 roles that this date dimension is playing. And now with that, we can analyze both the orders received, so based on the date dimension of the month. But now if we want to use the other role, so the other relationship or the other join with the other column, then we can also display the products based on the date of the production, so when the production has started. So in this case, we just use two different relationships. For example, if we are in Power BI or in Tableau, in any other BI tool. Or we can also, if we are just in SQL analyzing the data, use different joins. So once we just join this date table with the production foreign key, and the second time we join the same date dimension with a different date key. So for example, let's see how this looks like in practice. We have seen that we use different BI applications. The most common one is probably Power BI. In this case, we can set up our data model and we can set up relationships between our tables. And in this case, we can create one active relationship. So this will be the default relationship. We can just drag and drop, for example, the month and then the orders. So we can count the orders and then the default relationship will be used. But then we can also change that and use the inactive relationship in some of the calculations, some of the columns. So this is, of course, we are not diving into how this works now specifically in one specific tool, for example, Power BI, but this is the principle and how this role-playing dimension can be referenced multiple times. So by different foreign keys in one fact table. So this is possible in the BI tools. But also in SQL, we can create, this is how we should usually do it. If we want to analyze the data a lot in SQL, we can also create an additional view for each of the roles that this date dimension is playing. So for example, in our case, we can just set up a second view. A view is something that is just basically referencing a physically available table, but it is not physically available. So it has a new name and it appears like a separate table, but in fact it's just referencing the original physically available table. And with that, we don't create duplicate data, which is of course not so nice because it's redundant data, but it still appears as a second dimension that is dedicated for example, the production start date. And with that, we can create multiple joins and we can now use this dedicated view for the role this view is dedicated to. So to summarize things, this role-playing dimension is commonly used if we have a date table, so this is the most typical case, and we have in our fact table multiple references to this same dimension, for example, the same date dimension. But we can still implement that by having, for example, in BI tools then active and inactive relationships, or if we are analyzing the data mainly on SQL, then we can also create additional views for each of the roles, which just makes it easier for the analysts to analyze the data. So hope it was helpful and see you in the next lecture.